Okay, welcome everyone. So in this video, we are going to consider the span of two vectors in R3, the vector 1, 0, minus 2, and the vector 0, 1, minus 1. And the question we want to determine is whether or not each of these vectors in 1 and 2 lie within the span of these two vectors. So let's begin with question 1, which is asking us, is the vector 6 minus 2 minus 1, is that in the span of these two vectors, 1, 0, minus 2, and 0, 1, minus 1? So to answer this question, we can set up a vector equation. So I want to know, is the vector 6 minus 2 minus 10, is it possible to write that as some scalar x1 times the vector 1, 0, minus 2 plus some scalar x2 times the vector 0, 1, minus 1? So let's set up the augmented matrix to go along with this. So the first column, we have the coefficients for x1. Column 2, we have the coefficients for x2. And then we have our constants on the right side of the equation. So we're going to do some row operations on this. And so far, I've got my pivot column over here. So I'm going to solve this, by the way, by taking this matrix and writing it in its reduced row echelon form. So we have a pivot over here, that's great. And below it in row 2, I already have a 0. So the first operation I want to do would be to make this entry over here 0, so that all of the entries below this first pivot are 0. So I can do that with a replacement operation. Namely, we're going to replace row 3 with 2 times row 1 plus row 3. And the result of that would, again, give us a 0 over here. We still have minus 1. And then this last entry, we would take the 2 times the 6, which gives us a positive 12, and add to it a minus 10. And that's where this 2 comes from. And now we continue the process. We want to eliminate the entry below this pivot. So I can simply add these two rows together, and I replace row 3 with the sum of these two rows, which gives us 0, 0, 0. And so now this matrix, we started with this augmented matrix. It's row equivalent to this matrix over here, which is now in reduced row echelon form. And from this, I can see, well, I get no information from this bottom row. From row number 2, I can see that x sub 2 should equal minus 2. From the top row, x1 should equal 6. So that gives us our result. x1 is equal to 6. x2 is equal to minus 2. So therefore, we can check this, that if I take 6 times the first vector, 1, 0, minus 2, and then minus 2 times the vector 0, 1, minus 1, do I indeed get back this vector 6 minus 2 minus 10? And yes, we do. So that is a yes for this vector over here. This vector is in the span of the vector 1, 0, minus 2, 0, 1, minus 1. And you may solve this in a different way. So actually, in this case, it's not necessary to go through this row reduction. If I want to get a 6 over here, and I'm taking a linear combination of these two vectors, the only way I get a 6 in the first entry is if x1 is equal to 6, right? Because I can't get anything in the first entry from this second vector. And then you can say, okay, well, the only way I get a minus 2 in the second entry is if this x2 was equal to minus 2. And then you'd want to check to make sure that if this were equal to 6, that works for the top entry. If x2 were equal to minus 2, that's going to give me this entry. And then you would just want to check that 6 times minus 2 plus a minus 2 times minus 1. Does that, in fact, give me this one over here? And yes, it does. Okay, so next, let's look at the second vector here. So part 2 is saying, well, what about the vector 4, 5, minus 1? Is this in the span of the vectors 1, 0, minus 2, and 0, 1, minus 1? And so the corresponding matrix equation of this question I've written out over here. So can I find some scalar x1 times this plus some scalar x2 times the second vector 0, 1, minus 1, that when I add those two together, I get 4, 5, minus 1. So we could take a very similar systematic approach, which set up the augmented matrix, perform elementary row operations, to put it into reduced row echelon form and then try and make some conclusions based on that. But I will take kind of the more inherent view of this, which is, okay, if I want to get a 4 over here, then the only way that's going to happen is if x1 is equal to 4, right? Because I have a 0 in this vector. And if I want the second component to equal 5, well, since this vector has a 0 in this place, the only way I get a 5 is if x2 were equal to 5. So that's going to give me the first two coordinates, the 4 and the 5. The question is that going to wind up giving me a -1 in the third component? So if the third component, I would take my 4 times 2, and then I'm going to add to that my x2, which happens to be 5, times -1. So this is going to give me 8 minus 5 is equal to 3. So this does not give me -1. So here I can see that this vector does not sit in the span of the vectors 1, 0, -2, and 0, 1, -1. If you want to try and practice your elementary row operations, I would definitely encourage you to set up the augmented matrix, do your row operations on that matrix, and the resulting reduced row echelon form, you should find out that you have a pivot in this third column, and that's when you have an inconsistent system, and that would tell us in another way that this vector does not sit in the span of the two vectors that we started with. So on the previous video, we kind of ended asking for a geometric interpretation of what this set might look like. And so what we can see is that there are vectors in here that are not just simple, that don't sit on a line, but we're not getting all vectors in R3. So the space that's spanned by these vectors is not one-dimensional, it's not three-dimensional, so we might expect that we get a two-dimensional object embedded in R3, and that's exactly what happens. And so I've drawn a rough sketch up here where I've got R3, and rather than start these vectors at the origin, I'm just going to choose to start these vectors up here so it's easier to draw. So in red, I've drawn the vector 1, 0, -2. I'm going 1 unit to the right, 2 units down, and no units in the x2 direction. So that's this vector over here. The vector 0, 1, -1, I've drawn in blue. So this is not moving any units in the x1 direction, but it's going 1 unit in the positive x2 direction and 1 unit in the negative x3 direction. And what I get when I think about the span of these two vectors is actually any vector that happens to sit in the plane spanned by these two vectors. And this plane extends out indefinitely in both directions. So the span of these two vectors is going to be a plane in R3. So a two-dimensional space embedded in R3.